APRG seminar. So it is my pleasure to introduce today's speaker, Juyoung Lee from Korea Institute for Advanced Study. The title of his seminar is Variational Inequalities for Two Parameters, Averages over tori. So with this, I would like to invite him to deliver his talk. Also, I request all the participants to mute their microphone. Okay, over to you, Juyoung.
Okay, now I'll start. First of all, I want to thank to Kala-chan and Luna for inviting me this very nice seminar, and also to everyone who organized the seminar and participated in this seminar. Okay, my topic today is variational inequality and for some average. I guess some of here are familiar with some kind of maximal average, or some kind of bilinear maximal average. So my research topic has been around some kind of maximal average, but in this talk I consider variational inequality. It is somehow new object, but I'll explain what is the variational inequality first. But variational inequality is some kind of generalization of maximal average. Okay, and this talk is based on a work with Professor Sang-Young Lee and Fang Zhang. Okay. Okay, now first I will define what is variation. When I first heard the word variation, the two things came to my mind. That the first one is the total variation in real analysis course, and the second one is calculus of variation in PDE or variational method. Both things are somehow related to this our variational estimate, but the former one, the total variation, is more deeply related to our variation. So let's record that what is total variation. Roughly speaking, it captures the amount of fluctuation of a function. Let's suppose our function is, as in this graph, the black line, a black curve, and the total variation for this function measures the height of this valley in the graph. So of course we take the supremum, and it really measures how the function oscillates. Okay, then this total variation is referred to as one variation. So we want to generalize this total variation. So let's assume we have a function a here, defined on a set I, which is a subset of a real number r, and we choose a fixed number, finite number r. Then the one parameter r variation is defined by this equality. Okay, let's see. When r is equal to 1, this is just the total variation. We consider the literal error r summation rather than just the summation. So this is some kind of error norm of the total variation. Precisely speaking, we choose any partition T1 to Tn of I, and we calculate the difference of the value of A at Tj plus 1 and Tj, and take our literal error norm. Okay. And now we want to define a variation for a family of functions. We have a family of functions whose...
Okay, so one small thing, this r comma 1, what does this 1 stands for? R is
okay. Sorry, I forgot to mention it. Yeah, this 1 means this is the one parameter r variation. And in this talk, I want to define two parameter variation. This is our main object. So this one is for emphasizing that this is one parameter r variation. Okay.
Okay.
Yeah, thank you for asking. Okay. Okay, we now have a family of functions ft whose parameter is t and whose variable is x. So we can define a variational operator VR for a family of function ft. I need to emphasize that x is a variable of ft and t is a parameter of a family of functions. In other words, if we fix x here, then our ftx is no more a function, it's just a value of a function. So ftx is, the family of ftx is a function defined on I. I is the index set. Then for each x, we can define the one parameter R variation. So then eventually we get a function in x. So this is how I define the variational operator for a family of functions. And the study of this variational operator was initiated from the algorithmic theory, precisely the pointwise convergence problem of the algorithmic theory. I'm not an expert in algorithmic theories, so I will just briefly explain what it is and what is the consequence of the variational estimate. Okay, let's just say X is a probability measure space, which means it has a measure and the total, measure is positive, of course, and the total measure is 1. And we suppose tau is the measure preserving invertible transform from X to itself. For example, when X is the Euclidean space, tau can be just a translation or the orthogonal transformation. Okay, now we consider the average A and F here. We have a measure preserving map tau, so we repeatedly compose tau. We repeatedly act tau to x. So we have tau kx. So we take the summation from k between 0 and n-1. So the total number of this term is n. So we divide it by n. So this a and fx is kind of averaging. In this case, the index that I is the natural number, and the variational operator is defined by this equality. This is just following the previous definition. Okay, the very standard argument says that when we can consider the variational operator, then I mean when we estimate VR in the sense that this operator is bounded on LP space for any finite p, then the limit exists almost everywhere. But this limit does not have to be at just fx. It can be different from fx. For example, when x is circle and tau is the rotation by angle pi, then it is easy to see that tau square is just an identity. So if we consider this average, then when n goes to infinity, this average converges to fx plus f tau x over 2. So it is not fx in general. So this result implies that this limit exists almost everywhere, but it does not have to be fx. Okay, why we study variation? There are 3 regions. So the LP boundedness of the maximal function, this is the maximal function. This already implies some kind of pointwise convergence result. But why we consider variation? It is because this average is very simple because we only consider tau k, where k is just an integer. Rather than using this the simple composition, we can consider a polynomial in k. So I mean, we can consider this kind of average here. We consider k square here, but just LP boundedness of the maximal function does not give an algorithmic theorem for this kind of average. To handle this average, we need to handle the variational estimate. With some nice variational estimate, it implies this kind of average also converges almost everywhere. Okay, this is the first region. The variational estimate can handle more general algorithmic theorem. Okay, then this is the second region. While the bounds on the maximal function gives the qualitative consequences to the pointwise convergence problem, I mean, if we can handle we can get a nice estimate for the maximal function. It implies some pointwise convergence result, but it is only a qualitative consequence. But if we have some nice variational estimate for the variational operator, then it gives quantitative result. I mean, it gives information on the rate of convergence. So it is much more stronger than the maximal estimate. So this is the second region. And third region is very natural. We have the trivial inequality that the maximal function is bounded by the variational function with some trivial term. So from this trivial inequality, the variational estimate is stronger than the maximal estimate because the variational estimate implies the maximal estimate. Okay, this is 3 reasons why we study variation. And now I'll explain some historical remark on the variational inequalities. As far as I know, the result by Leffinger in 1976 is the first nice result on the variational inequality. He proves very general result. He proves that for any bounded martingale sequence Fn, the variational operator Vr is bounded on LP space when R is greater than 2 and P is between 1 and infinity, excluding 1 and infinity at the endpoint. And it is also well known that when R here is less than 2, then the variational estimate is impossible. So Leffinger's result is somehow a sharp result. But he only considered
Sorry, what did you say? When R is less than 2, what is the thing?
when R is less than 2, then in general the variational estimate is impossible. Always fail.
It is unbounded, right?
Yeah, right, unbounded for any P. So this is somehow a sharp result. So
okay, I have a small question here. If suppose R greater than 2, what about this endpoint 1 case?
What do you mean endpoint? R equal to 2?
No, R equal to 2 and P is equal to 1, P is equal to infinity.
P is 1 and infinity.
So there are many cases. Okay.
Yeah, right. There are many cases. I've not seen any result on P equal to 1 or infinity, but when R is equal to 2, the next result by Bourgain in 1989, he obtained the endpoint result somehow. Yeah, for L2 space. Okay. When we consider this kind of simple ergodic average, then for this kind of average, the variational operator is bounded on L2 space when R is equal to 2. And a few years later, Jones, Kaufman, Rosenblatt, and Wilder obtained a more general result than Bourgain's result. They proved that in the same setting, the variational operator is bounded on LP space for any P between 1 and infinity and R bigger than 2. Okay. Where I also remark again that using the variational estimate for this simple ergodic average, we can obtain the pointwise convergence result for this polynomial type ergodic average. That is why Bourgain wanted to obtain this variational estimate. And now people who study variational estimate does not have interest in just ergodic theorem. At least for me, I am just only interested in the variational estimate itself. I think Jones, Kaufman, Rosenblatt, Wilder also same with me. They considered the variational estimate for a slightly more general setting. And later, Jones, Siegel, Wright in 2008, they introduced some basic scheme to prove some variational estimate, and they applied their method to obtain some variational estimate for very famous operators in harmonic analysis, such as the spherical average. They obtained the sharp variational estimate for the spherical average, and also they obtained the variational estimate for the truncated Hilbert transform, an average over degenerate curve, or a truncated singular integral operators, and so on. their method can be applied to many interesting operators. Okay, and they proved that their result is sharp, and they proved that the variational estimate is bound. Variational operator is bounded on LP space when PR satisfies the suitable condition, but it is very complicated. Okay, this is our historical remark. Okay, so today's topic is two-parameter variational estimate. So I will mention some historical background on the multi-parameter variational inequality. So I already mentioned that the variational inequality was initiated to study some algorithmic problem. So this multi-parameter variational inequality is also started from getting a solution for the multi-parameter algorithmic theorem. So in the one-parameter setting, X is just the probability measure space, and we only have one measure preserving invertible map, tau. So, but in this case, we consider multi-parameter case, so we have many measure preserving invertible maps from X to itself, of course. When we have D measure preserving maps. So in this case, it is the D parameter algorithmic problem. So for any vector n with D components, we define D-dimensional algorithmic average like this. We take summation for all ji between 1, 0 to ni, and we need to define some lexicographical order to this vector n. So we define the partial order m. Vector m is less than or equal to vector n if each coordinate of vector m is less than or equal to the corresponding coordinate of the vector n. Okay, it is natural, but it is not the complete order. It is, of course, the partial order. So the associated algorithmic problem is that when each coordinate of the vector n, I mean or n1 to nd goes to infinity, then we want to ask that the limit of this average converges to something for almost everywhere. Of course, I want to emphasize again that the limit does not have to be fx. Okay, in this case, the corresponding variational operator to handle this algorithmic problem is defined by the following, where this supremum is taken over all increasing sequences of vectors in ZD. I mean, increasing is defined by this partial order. Okay, so this definition is very natural, and if we can handle this variational operator, then it is enough to handle the multi-parameter algorithmic theorem. And we can also consider the polynomial type algorithmic theorem by using this variational operator. In 2000, Jones, Rosenblatt, Wilder obtained a sharp result on this variational operator that it says when R is greater than 2 and P is between 1 and infinity, this operator is bounded. Okay. But to me, this variational operator is not enough, because at the beginning, I mentioned that variation is the mathematical object that measures the oscillation of a function. But this definition of the variational operator does not measure all oscillation of the function, as we can see in this picture. We consider two-parameter case first. In two-parameter case, we only have vector n is n1 and n2, so we only have two parameters. So these red circles are increasing sequence of vectors. So in the definition of the multi-parameter variational operator, we only consider the values of the function along this something like curve, but we don't use any information in this empty area, question mark here. So if we want to measure the all oscillation in the domain, we need to consider every information in this blank region. That is why we need to define a different variational norm. And this is our intuition. Okay, let's suppose A is a function defined on this square, 0, 1 square. And I and j are partitions of the interval 0, 1 respectively. And when we have two partitions I and j, then by producting these two partitions, we can obtain the partition, we can naturally obtain the partition on this square. Okay. There is already some kind of some generalization of Hardy-Krauss total variation, which is called Hardy-Krauss variation, which is defined by A times this rectangle, A with this rectangle. I will define this quantity soon, and we take the summation and take the supremum for all partitions I and j. Okay. In the partition of 0, 1 square, each pieces are rectangles. So we have a rectangle here. So let's say ij is t1, t2, and jk is s1, s2. Then we have 4 corners. We want to use all information of these corners. So instead of just using the difference of these two, we consider 2 pluses on this right upper vertex and the left lower vertex, 2 plus, yeah. And the left upper vertex is minus and right lower vertex is minus. Okay, then we have some kind of this alternating sum. Okay, so Hardy-Krauss variation is defined by this this quantity. So generalizing this Hardy-Krauss variation to R variation, we just consider the little error summation to this setting. So that is how we define two-parameter R variation. It really uses the OR, it really measures the OR oscillation in the domain. So now our function is A, and it is defined on our rectangle I times J. And I suppose I alpha comma beta is the lower left vertex of I times J. But this definition of the two-parameter R variation is not enough for the pointwise convergence problem. For a technical region, if we want to get a consequence of the pointwise convergence result, then we need to define a slightly bigger R variation. Here, this 2 means this is the two-parameter variation. Okay, but finiteness of this two-parameter variation does not imply the pointwise convergence. To get a pointwise convergence result, we need to handle that. We need to get finiteness of all of these 4 terms. These 4 terms. Okay, let's see what are them. This is the value of the lower left vertex of the domain, and this is the one parameter variation of the vertical side of the domain, and this is the horizontal side of the domain. I'm sorry.
I think someone has to mute his microphone.
Okay.
Just wait.
Okay. Yeah. Okay. Our two-parameter R variation is defined by summation of these 4 terms. Anyway. Okay. We can alternatively define two-parameter variation because someone may think that this definition is not natural. So naturally, we can define this kind of natural definition. We consider any partition of I times
Can you
J.
just go back to the previous phase a little
Okay.
bit? This variation you are taking for this so that pointwise limit will exist, right? Finiteness. Okay, so you are restricting this thing. Okay.
Okay. Thank you. Okay, we may use another natural definition. This OSC means oscillation. So this is called oscillation norm. So now we consider any partition of I times J. So any partition, but it is not actually any partition. It is the partition by rectangles. So for each rectangle, there is upper right corners and the lower left corner. So we call them RQ and LQ. So we consider difference of the values of A from the upper right corner and the lower left corner. So of course we take our literal error summation and taking the supremum over all partitions. But we can easily find the counterexample that when if we define the variation operator using this oscillation norm, then the variation operator is never bounded on any LP space for any R. So this two-parameter oscillation is useless, actually. Yeah. Okay, of course. And in our two-parameter R variation, we considered independent partition of interval. We considered partition ij and partition jk, and we producted these two partitions and obtained the partition in the rectangle. But we may use any partition pij instead of partitioning I and j independently. But this alternative definition gives essentially comparable value of the variations. So it is why we only consider this simple partition by partitioning I and j independently. So they're essentially equivalent. Okay. Now we come to our main object. Maybe someone remember my topic, the title of my talk. The title of my talk is Variational Inequality of the Average over tori. So I want to explain what is the average over tori. Before that, I want to mention the very important result on the maximal average on a sphere. So, okay. The sigma is the normalized Lebesgue measure on a sphere as D1, D-1 contained in RD, Euclidean space, and it is centered at the origin. Then the spherical average is defined by this equality, and this calculates an average of a function f on a sphere centered at x with radius t. And it is well known that if we take supremum for this average over all positive radius t, then this maximal operator is bounded on LP space if and only if p is bigger than d over d-1. This is very famous result in this area. So this is why I might want to mention that. And we record the definition of the variation operator. Using the definition of the variation operator, for this spherical average, we can define this variational operator for the spherical average. Okay, we also record that the maximal function is bounded by the variational operator plus some trivial term. So it means the variational operator is more difficult to handle than the maximal function. Okay, in 2008, Jones, Siegel, Wright obtained a sharp.
So this R is NER, or there is any restriction for this?
Yeah, for definition, we can consider any R bigger than 1, bigger than or equal to 1. Yeah, but
so for this maximal function is bounded by. Okay.
Yeah, but if we want to get some boundedness result, we need to restrict R bigger than 2.
2.
But we don't know the endpoint result. Okay.
Okay.
There is no result on the endpoint result. Okay. Anyway, in 2008, Jones-Siegel Wright obtained the variational estimate on LP space when R is greater than 2, P is greater than this number. This number comes from the boundedness of the maximal function. And also R and P satisfies this relation, this inequality. And these three conditions can be visualized in this picture. So the point 1 over P, 1 over R should be contained in this blue region. If this point is at the outside of this blue region, then this operator is not bounded. Okay, this is the important result. And now I will define the average over a torus. Torus is kind of generalization of the circle because topologically, torus is the product of two circles. So I will define a suitable Lebesgue measure on our torus embedded in R3. So you just imagine the shape of donut.
Can you go back to the previous result a little bit?
Okay.
previous result?
It's
The
done?
theorem. Yeah. Not in the closure of the region.
Yeah. We don't know anything on this boundary. So
Okay. So boundary, yeah, E greater than D by D minus. Okay. Thank you.
Okay, thank you. And okay, now you just imagine the shape of the donut embedded in R3. The donut is torus. So topologically, it is the product of two circles. We have two parameter T and S for this torus. And if we suitably define the Rubin measure on this torus, we can define an average as before. So this looks a bit complicated, but this is just an average of a function f on a torus centered at x with two radii t and s. We can naturally define the two maximum functions by the second one is more natural. We can take the supremum over t or t and s, but to make this embedding smooth, we need a further condition that s is less than c0t, where c0 is a fixed number less than 1. And also, if we fix the ratio between t and s by c0, then we can consider a one-parameter maximum function first. So we have two maximum functions. The first one, m1, is one-parameter maximum function, and the second one, m2, is the two-parameter maximum function. And it is very natural to guess that the range of P, which makes this maximal operator bounded, should be different for M1 and M2. But myself and Professor Sang-Young Lee obtained this result, but we obtained this result in 2022, but it is published this year. Anyway, we obtained that both M1 and M2 are bounded on LP space if and only if P is greater than 2. We also obtained some sharp LP-LQ estimate, but I don't want to mention this result because it is complicated and it is not related to this topic. Okay, anyway, we obtained a sharp result for this maximum function. And our main object in this talk is considering the variational estimate for this average on the torus. Okay, this is our first result. Before going to our two-parameter variational estimate, we first consider one-parameter variational estimate for this average. I mean, one parameter means we fix the ratio between two radii, t and c0t. So, okay, in this case we only have one parameter t, so this is why we can consider the one parameter variational estimate. Anyway, this is our first main result. This one parameter variational estimate is variational operator is bounded on LP space when R is
Can you just go back to how did you define this thing? A T C0T in this setup? Oh, T one only just. Okay,
this is typo anyway. Yeah. Okay.
Okay, I understand. Okay.
This is typo. And this is bounded on LP when R and P satisfies these three conditions. These three conditions can be visualized as in this picture. So 1 over P, 1 over R should be contained in the interior of this quadrilateral. And if this point is at the outside of the closure of this region, then it's not bounded. So it means this result is essentially sharp result. Okay. And unfortunately, we don't know anything on the boundary. Okay. Yeah.
Excuse me, I have a question. Sorry to disturb.
Okay.
Yeah. What is C0 in this?
C0. I want to draw a picture and visualize to you, but
this
I
is
cannot.
Constant.
Yeah, this is a constant.
So he is
any constant?
We have two parameter T and S naturally, but to make this, I said that this torus is embedded in R3, but to make this embedding smooth, we need a further condition that S is less than C0T, where C0 is less than 1. So
less than 1.
In one parameter setting, I choose S to be C0T itself. So that is how I get one parameter. Anyway.
Thank you.
Okay. Okay. Thank you. Thank you for asking. And in summary, we obtained some sharp result for this one parameter variational operator. Okay, now we turn to the two parameter variational estimate. Our two parameter is contained in this domain J, defined by the interval 1 to 2 times this interval. Okay. Record the definition of the two parameter variation. This two parameter variation is the summation of 4 terms. This is just the average with fixed radii, and this is the one parameter variation, and this is the one parameter variation again, and this is the two parameter variation. Okay, and from this definition, we define the variation operator, and this variation operator is bounded on LP when P1 over P, 1 over R is contained in the following region. This is the following region, okay? When 1 over P, 1 over R is contained in this blue region as well as in this green region, then the two parameter variation operator is bounded. And also, if the point 1 over P, 1 over R is at the outside of the closure of this region, then it is not bounded. So this is also an essentially sharp result. Unfortunately, again, we do not have any endpoint result now. Okay, I want to emphasize P5 here. P5 is this point. So this blue region is the sharp range for the one parameter variation. And it is obvious that the two parameter variation is bigger than one parameter variation. But in the maximal function, one parameter maximal function and the two parameter maximal function have the same boundedness property. They are bounded if and only if p is greater than 2. They have the same boundedness property, but in the variational estimate, they are different. Okay, P5 here. The one parameter variation is bounded in the region P1, P2, P3, P5. But if you consider two parameter variation, the amount of this triangle, white triangle, P4, P5, P6 is excluded. This is the difference. So anyway,
sorry, what about this green region? It is bounded.
Yeah, green region and blue region. Okay. The two parameter operator is bounded anyway. Yeah, okay. These together because I distinguished these two regions because the proof method are different.
Yes.
And now I want to explain the key estimate in the proof, but it is very brief and it is somehow technical, so it will be quite difficult to understand, but I will try my best. Before giving an idea of the proof of our theorem, I first give some idea on the one parameter variation for the circular average, which is due to Jones-Seeger right. Okay, we assume that R is less than P for simplicity, because when R is bigger than P, it means that 1 over P, 1 over R is is under the line P1, P3, the diagonal line. But under the diagonal line, we don't have any interesting feature here. And we obtained the result under this diagonal line by the trivial embedding. So that is why we only consider the point above the diagonal line. Okay. And this is very important. By the sublap embedding, we can remove the variation operator and taking the in the maximal function, using the sublap embedding, we can remove the supremum and get the LP norm by the cost of 2 to the j over p, where this pj is the Littlewood-Paley projection. I mean, pj, the Fourier frequency of the pjf is restricted in an annulus of radius 2 to the j. Okay, so this is the Littlewood-Paley projection, and if we consider the maximal operator rather than this variation operator, we can use the sublap embedding and obtain the loss 2 to the j over p. But in the variational setting, we get, instead of 2 to the j over p, we get 2 to the j over r. And we assumed that r is less than or equal to p. So 2 to the j over r is bigger than 2 to the j over p. It is very natural because the variational operator is bigger than maximal operator. So we get a bigger loss. Okay, this is very natural from the overlap embedding. And since r is less than or equal to p, we use the Hölderlin inequality to this t integration and obtain this estimate. So we have the LP norm in both x and t. So now p and the exponent for x and t are identical. We can use the local, well-known sharp local smoothing estimate for the wave operator, and we obtain this kind of estimate. This is the sharp local smoothing estimate for the circular average. And combining these two estimates, we can obtain the region as in the result of Jones-Siegel-Wright. Jones-Siegel-Wright is here. We can obtain all sharp region here by using local smoothing and the overlap embedding. Okay, now we can apply this method to our setting, two-parameter variational estimate. But in the two-parameter variation, it gives only the blue region in this region here. So this is why I distinguish two regions, green and blue. Using the method of Jones-Siegel-Wright, we only obtain the result in this blue region. But to obtain the result in this green triangle, we need to get some more information. That is our main novelty in our result. Okay. The reason why we cannot obtain the sharp result using the local smoothing estimate is because we use the trivial Hölderlin inequality here. We need to directly handle the sharp estimate for this mixed norm estimate rather than using the Hölderlin inequality and the local smoothing estimate. So in this Hölderlin inequality, we lose too much. So we should not use the Hölderlin inequality. Okay. Our main idea is using the square function estimate to get a sharp range. But this square function estimate is not the famous square function estimate. It is slightly very different. Okay, what I mean the square function estimate is we want to get this estimate. Here, this is the mixed norm. We take LP norm in X and we take L2 norm in TNS. Okay. We want to get a sharp estimate for this kind of square function. And of course, we can simply use Hölderlin inequality again that and obtain this L2 norm in TNS is bounded by LP norm of TNS, and also applying the sharp local smoothing estimate. But again, it is obviously not sharp. Instead of that, we directly handle this square function. To do this, we use the following equivalence by using the asymptotics of Bessel function. It is very standard method in the maximal function and variational estimate. I don't want to mention it precisely, but anyway, just to believe this, we have the following equivalence. This averaging operator with frequency restriction, we have some kind of this term, and this decay comes from the decay of the Bessel function and we have this propagator operator. We denote this operator by WJK. This PJK is a frequency restriction, but where our torus is embedded in R3, so this xi is contained in R3. So xi bar means the first two coordinates of xi. So this is equal to xi1 and xi2. And xi is xi1, xi2, xi3. Okay. This frequency restriction is the restriction to annulus again, of course, and we restrict the size of xi bar to the 2 to the j and size of xi to 2 to the k. So when xi3 is very large, then this frequency restriction becomes some kind of weird region anyway. But it is technically important to define this projection like this. Okay, now the method is reduced to obtain a sharp estimate for this propagator operator, because we have that the averaging operator is equivalent to the propagator operator with this decaying term. Okay, and it is easy to see that if you have some kind of this estimate, then the sharp constant C should be greater than or equal to 1, comparably 1. But when P is equal to 2, the method using Hölder's inequality is sharp. I think it is confusing, of course, but since we cannot obtain better than epsilon loss, and we have sharp local smoothing estimate by Gusu-Wang-Zhang, and it only loses epsilon loss. And Hölder's inequality, of course, does not lose anything. So we obtain this estimate where C is equal to 2 to the epsilon j for any epsilon. So when only for P equal to 4, we get a sharp result using the Hölder's inequality and the local smoothing estimate. So by using interpolation, if we can obtain this kind of sharp L infinite square function estimate, then by interpolation with this estimate, we obtain the sharp square function estimate for the propagator. And this is a typo. This should be replaced by WJK. Okay, I'm sorry for that. Okay, now some complicated technical thing again, but using Planck-Charles theorem, we can replace our propagator again, and we suffices to obtain this kind of L infinity estimate where SJK is defined by this square function. Okay, and this PJK tau sigma is the Fourier restriction F in the following region. Now this is the region where basically tau and sigma are the frequency variable in of TNS. So since we use the Planck-Charles theorem to TNS, we don't consider a variable TNS anymore. We consider the frequency variable for TNS, and I called them tau and S. Okay, in this setting, this projection PJK tau sigma is defined by the Fourier restriction again. Okay, and that region is defined by the intersection of two regions. The first is this green thin cylinder. The radius of this cylinder is sigma, and the width of this cylinder is 2 to the minus j, and this is the sphere in R3. This is the second region. The thickness of this sphere is depending on j and k, but it is not simply 2 to the minus j or 2 to the minus k. Anyway, this projection is the Fourier restriction of F into the intersection of this green region and this black region. Black region is the small neighborhood of the sphere. Okay, and this intersection is actually the thin cylinder anyway. So in psi3 variable, we use the Bernstein's inequality, and in xi1, xi2 variable, we use the sharp local restriction estimate for the circle in the plane. So I think this is very technical, so maybe many of you cannot understand, but this is what I can do best anyway. So anyway, in summary, to get a sharp estimate for the averaging square function estimate, we replace this averaging operator by the propagator operator. And by using the Planck-Charles theorem, I replace this propagator operator by this kind of square function operator. To handle this square function operator, we use the local restriction theory and the Bernstein's inequality. So that is how we get the sharp result here. Okay, and finally we get this kind of square function estimate, and we already have the sharp local smoothing estimate. So by interpolating these two estimates, we obtain a mixed norm estimate, LP, LR, LP estimate for a sharp C, sharp constant C. And we record that by the sublap embedding, we have this. Actually, we need to use sublap embedding twice because we have two parameters. So we applied two sublap embeddings, and in the first sublap embedding, we obtain 2 to the j over r, and in the second sublap embedding, we lose 2 to the k over r. So that is why we have this constant. And by using sublap embedding, we can replace the variation operator by the LR norm of TNS. And we already have the sharp mixed norm estimate for these averaging operators. So combining everything together, we obtain the sharp variational estimate. So using this method, we can cover this green region. So I also mentioned that this region, green and blue region, are sharp of the boundary. So that is how we obtained the sharp two-parameter variational estimate. Okay, this is all. Thank you for your attention.
Thank you, Juyoung, for a very nice talk. So, is there any question from audience? Yeah, Kalachan, you can go ahead.
Oh,
Yeah.
no, it was.
You have question, Kalachan?
No.
So I have one question. When you define this M1 and M2, so
M1 and M2 is
you
the
take
maximal
this S
operator
by T.
here.
Yeah, no, S by S by T is this one. S by T less than C naught and S by T greater than C naught. That's what you are taking, right?
Right.
Okay. So why you are taking such type of operator? I don't understand this.
I'm sorry again, please. Pardon me.
So in the definition of M1 and M2, okay, there are two parameters, S and T, right?
Right.
T and S, but you have taken this S by T less than C naught.
Right.
In M1.
In M1, C0T
Yeah.
here. Yeah.
M2 is less than S by T less than C0. Sorry. In M2, you have taken S by T less than C0.
Right.
And okay. So why did you define this operator this way, M1 and M2? What is the reason?
It is because the embedding of this torus in R3 is not smooth when T is equal to S. So first of all, we need to restrict the region of TNS by S should be less than T. But for the technical region, we need to get some more than that. So this is why I restricted S less than C0T, where C0 is less than 1, a fixed constant. So the base, in summary, the region is to get a smooth embedding. Okay, thank you for asking.
Okay, so the thing is, so this result is sharp, right? This M1, M2 are bounded on LP if and only P greater than 2.
Yes, this is a sharp result.
Okay, and what about can we go back to the previous slide maybe?
Previous slide here.
This maximal operator, previous slide.
Previous.
Again, previous.
Previous.
Yes. So this is
Which one?
that. So can you go back next slide probably?
Next one.
Yeah. Next. Yeah. Okay, so yeah, just keep in this thing.
Okay.
DP is getting no.
This
Previous
one?
slide, just No, this just previous slide. Sorry.
Previous one.
Yeah.
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 Yeah. I mean,
yeah,
you mean
just
this result?
yeah, this one.
Yeah.
This is bounded on LP and if and only fit. Okay, so yeah. Okay, okay. This is yeah. This there is a result by this. What is that name? Leipzig and Jones or something.
Here, maybe here.
Yeah, Jones. Okay, so this for yeah. So for this is okay. This is 98. Okay, so this they have extended this to higher dimensional algebra, right? This Jones result, which you are really
Higher dimension.
no, a D variation or something.
Yeah, D
Mu
variation
what?
something. Yeah, right.
On
D variation
LP,
something is here.
Okay, and X is
Jones
here
doesn't-
any major, yeah, any major space, not just.
Yeah, any major space. No, it should be a probability measure space. Yeah, I missed it.
Oh, probability. Okay, probability measure space. Okay. Thank you. I don't have any.
Okay, so I have one question.
Okay.
That operator M1, M2, you are defining in R3 only. So can one consider this operator in higher dimension? It will be more difficult, or
yeah, sure. But in higher dimension, we need to first consider the maximal function first, because there is no resultant maximal function in higher dimension of torus. Yeah.
yes, like this M1, M2.
Yeah, right. But it is using the same method in my paper with Professor Sang-Young Lee. We can surely obtain a sharp result. But for the higher dimensional torus, but it is just a technical thing, so I didn't do that. Yeah.
Okay, and the expected range should be P bigger than n over n minus. No, not it is. It will be something bigger than this.
Yeah, maybe if it is a product of S1, then in any dimension, the multi-parameter maximal operator is bounded when P is bigger than just 2. And it is a sharp result.
In any dimension?
Yeah, in any dimension. But
okay.
Yeah, I didn't write it in a paper, but yeah, I just believe that.
Okay, and for both M1 and M2?
Right, both M1 and M2.
You think the decay of the Fourier transform will be essentially like half? Or
yeah.
It is more technical.
Yeah, right. The decay of the Fourier transform of the measure is half, so that is why the range is bigger than 2. And maybe I'm not sure you know the Regent result by Seoul. He proved that when the decay of the Fourier transform is 1/2, then for any hypersurface in any dimension, the maximum operator is bounded on LP space P bigger than 2. Yeah.
Yes. Yeah.
So
yeah, one can use that result to maybe also. Okay. Thank you. Thank you for a nice talk.
Yeah, thank you for asking, and thank you for inviting me.
So
are there any okay. Do you want to ask any other questions?
No.
Yeah. So if there are no more questions, let us unmute and thank the speaker for very nice talk. Okay.
Okay, thank you very much.
Okay, so Kalachand, you may stop the recording.
Yes.
Did you stop the recording?
Yes.
Sir,